afternoon, everyone. Let's begin. This week we're taking a look at the Magdeburg Water Bridge. This is an aqueduct in Germany that actually connects two canals that allows shipping to go from Berlin into the heart of the Rhineland, which is a really heavy industrial area in Germany. And so as you can see, it is a water bridge that's crossing the Elbe River. It's pretty amazing to think that they were able to do that. It was expensive, though, $630 million, so hopefully they get their money's worth on improving the shipping costs between those two industrial areas. This week we are very fortunate to have a couple of great speakers, but before I introduce either of them, let's look at these announcements here. First of all, you had a presentation at the beginning of class last week about the engineering apparel that's available for you to purchase. If you lost your order form, they have more order forms over in the engineering building. They're just set out on a table over there. It's very obvious. And the little box that you're supposed to submit the order forms to, that's obvious. That's also obvious and well marked. So I'd encourage you to order that if you're interested. Also, quiz number 6 is going to be available within probably a couple of hours. Right now, I'll post it online, and then it'll be open through the 10th at 11 a.m. And just a side note, many of you have probably already noticed that I record these presentations, and so if you want to listen to it all over again before you take the quiz, you're certainly welcome. Or if you happen to miss class for some reason, if you're ill or have another reason to miss class, the recordings are posted. Of course, it's only if you have an excused absence that you won't be counted, marked against you on the attendance. But if you do miss class because of somebody's wedding or it's your grandma's birthday or whatever, at least you can watch it and take the quiz, even if you don't get attendance for that day. So that said, I'll introduce our speakers for today. First of all, we're going to have a faculty member introduction by Dr. Gregory Michaelson. He's one of the newest faculty members to join the College of Engineering, and we're very happy to have him, and he'll explain a little bit about his specialty area and the things that he does here at Marshall. And following Dr. Michaelson, Michael Audello is going to give an overview of his work at Rahal Transportation Institute. And he's a graduate of Marshall University. My first semester here at Marshall, he was in the very first class that I taught. So he's got a spot in my heart because I have fond memories of that first group that I taught hydraulic engineering to when I arrived at Marshall. So with that said, I'll turn the time over to Dr. Michaelson for his presentation. There we go.
All right. Let's see. Let's make sure the remote works. All right. Okay, so like Dr. Waite said, my name's Dr. Michaelson, and I'm the new guy here in the Department of, or the Division of Engineering. I've been here for about 2 months, and I'm essentially the structures guy. I'll be the guy teaching all the structural engineering courses that you have when you're a junior and a senior. So what I'm going to do today is I'm going to tell you a little bit about structural engineering in general, and then tell you a little bit about myself, what it is that I do, and talk about one of my projects that if you'd like, you may get a chance to be involved in sometime later on down the road. So to start out, like I said, I'm a member of the coolest field of engineers, the structural engineers. What is it that we do? Well, we essentially make sure that any structure that we build, mostly buildings and bridges, but anything that's, that is composed of anything that goes in the built infrastructure, we ensure that it is structurally sound, that it's safe to resist the loads that it's going to be subjected to. That's a pretty simple but general definition of what it is that we as structural engineers do, but it can get far more complex than that when you start to look at some of the structures that we build. But we do our best to try and simplify things by looking at it from two sides of the equation. So the first thing that we do when we're attacking any type of structural analysis problem is we start looking at the loads that our structure is going to be subjected to. So for instance, let's say that we were designing some of the floor beams in the room that you all are sitting in right now. Well, first thing we'd have to do is quantify the loads that those beams are going to be subjected to. So, number one, the beams would have to be able to resist their own self-weight and the weight of all the floor components. Second off, obviously, the beams would have to be strong enough to resist the weight of all of you. The beams have to be able to resist that. If we start looking at entire building systems, for instance, things like environmental loads, we have to make sure that buildings can withstand things like wind and snow. Another big topic within structural engineering that really doesn't affect us here in West Virginia, but can affect you in places like California or Japan or places like that, is the concept of earthquakes. Buildings have to be strong enough to resist that. So that's sort of the first side of the equation, is calculating all of the forces that structures are going to be subjected to. And then the second half is the resistance. When you all are in college getting your bachelor's degree, and if you want to go on get a master's or something like that, you'll learn about how steel behaves, how concrete behaves, how timber behaves, and things like that. And then once you determine how those materials and members behave, you can ask yourself, well, how large do those members need to be such that their strength is bigger than the loads? And that's basically all there is to it with structural engineering, but it presents sort of an interesting dilemma, okay? Let's say that all of you, let's say you are a bridge engineer, and you're working on a project where you're designing a bridge, let's say, in your hometown. And you know that once that bridge is finished, your grandma and grandpa are going to be using that bridge every day to go into town, to go to the grocery store, what have you. And you think to yourself, well, gosh, I don't want anything to happen to grandma, so when I design that bridge, I'm going to design it very stout. I'm going to use very large, deep beams and design a very strong structure. It creates a problem because while you've designed a structure that's safe and sound, you've also designed one that's very expensive. So I say this about structural engineers, but this would really be true about most engineering disciplines in general. We sort of walk a tightrope between safety and economy. Number one, we always have to design a structure that meets the safety of the public. The welfare of the public is always our primary concern. But once we meet that, we have to design a structure that's economical. And that's where the challenge of structural engineering comes into play. Now, I said earlier that, of course, structural engineering is the coolest discipline. Why is that? Well, stuff like this. I mean, for instance, let's say looking at the Burj Khalifa. Tallest building in the world, over half a mile tall. Now, don't get me wrong, a tip of the hat definitely needs to be given to the geotechnical engineers and the architects that worked on this project, but this project would not have existed had it not been for structural engineers. And we don't do stuff, just like tall buildings. I mean, we have things like stadiums, like the new Dallas Cowboys Stadium, and things like that. And you look at some of these projects and you think, well, how do you even begin to approach a problem like this? Because these structures are just massively complex and massive in general. But the way we tend to think about it is, while this structure is very complex and it has thousands and thousands of different members and components, it's still just comprised of beams and columns and braces and things like that. If you can design a beam or a column, you can design any beam or any column in a structure like that. So that's sort of our general strategy. We also work on bridge projects. This should be a fairly familiar one. New River Gorge in our state of West Virginia, highest arch bridge in the Western Hemisphere. This is an example of the type of things that structural engineers do. This is some more examples. You see a cable-stayed bridge in the top left. Got your Golden Gate Bridge and a lenticular arch as well. Just a little bit of info about later. Like I said, I'll be teaching most of the structural engineering courses, and this is the kind of stuff that I'll be teaching. Now, the first 4 courses, if you're getting a BSc with a civil emphasis, these are courses you're going to take anyway. So these would be the ones that would be these would primarily pertain to things like structural engineering or even geotech or whatnot. If you're interested in structures, maybe something to sort of keep in the back of your head for later, if you're interested in structures, you might want to consider taking steel design. Also, I'm not 100% about this, but hopefully by the time you all are juniors and seniors, I'd like to offer a course in advanced structural analysis, so you might want to consider taking that as well. A little bit about what it is that I do. My research area is specifically focused around steel bridges, and the long and short of it is what I try and do is make steel bridge design simpler and more economical. And I wanted to share with you one of the research projects I've got going on, because later on, if you all are interested, I might ask for some of your help in doing some testing for this project. This is a project that I've been working on for a couple years now, and I've brought my work with me here to Marshall University, and I'm sure you all have heard about the, well, I know you all have seen the new building that's being constructed. I'm not sure if you've heard of the new structural testing lab that's going in the back of that building, but I'll definitely be using that lab to evaluate this system. Now, a little bit of background about this system. This was an idea that was generated from members in the short span bridge industry to try and tackle the needs of our infrastructure. I don't know if you've been able to pay attention much to the state of our infrastructure, but when we look at things like bridges and whatnot, our infrastructure really isn't doing so hot. So we're really trying to come up with new and innovative ways to tackle that problem. This was a concept that we came up with that utilizes standard plates to fabricate a tub girder that you see right here. Now, the idea of a standard plate is kind of like the idea of lumber. You know, if you go to Lowe's and you ask for a 2x7, they're going to kind of laugh at you because there's no such thing as a 2x7. They come in standard sizes like a 2x4, 2x6, 2x8, things like that. Well, we used a standard plate, kind of the same idea, in order to fabricate a tub girder that you see here, and then just ship the whole thing to the site. These things are incredibly fast to fabricate. It usually takes a conventional bridge girder about a day to fabricate. It takes these under an hour. I watched one of these fabricated from start to finish. It took, I think, about 35 minutes, so it's incredibly fast. But it's new. It's a unique technology that nobody really understands how it works, and nobody really understands how strong it is. So how do you determine how strong it is? You test it. So for my PhD, I engaged in a large-scale experimental testing program looking at assessing how strong this system is. So to give you an idea about the scale, this is us casting a concrete deck on one of the specimens, and that's me casting the deck, to give you an idea of how big these things are. And this was the specimen when we were done, when we tested it. I'll sort of walk you through what we did, because you can see this was some really exciting work. This is sort of a slideshow of pictures showing the progression of a test from start to finish. So on the top left, you see this is the standard plate that was being formed into being formed using a large capacity press brake. You can see here they're forming one of these top flanges. What they would do after this is flip the girder upside down and make two bends about right here and about right here to form the rest of the tub. We shipped the tub to a structural testing lab and then erected formwork to cast a concrete deck. You saw me up there casting the deck, and this is what it looked like when it was done. We waited for the concrete deck to cure, and then we installed a series of instruments in order to measure its response. Up here on the top right, this is what's called a load cell. A load cell is really nothing more than a super duper fancy hyper accurate bathroom scale. Basically all it does is, as load's being put on it, it just measures how much force is on the ends of the beam. We've got a series of strain gauges here on the girder. This essentially measures how much stress is in the beam at a given point. And then in the middle of the beam, we had an actuator applying load. An actuator is just really a really accurate piston. That's a good question. And what I'll say is this: you really don't measure stress. Stress is an internal, it's just an internal distribution of force. But what you do is you measure strain. You measure how much it stretches, how much it deforms. I'll go ahead and talk about that real quick. Here on this girder you see a series of strain gauges. Strain gauges they're really just calibrated pieces of foil that have coiled up wire on it. And the idea is you pass a current through it. What happens is, thank you, you pass a current through it, so you pass, say, 10 millivolts in it. As the girder's being loaded, the wire's going to stretch. the voltage changes, and you take that change of voltage and you just back calculate how much the girder's stretching. That's a good question. And by the way, if y'all have any questions, please feel free to interrupt me. But yeah, okay. So right here in the center, this is what's known as a large capacity actuator. It's just basically a hydraulic piston. You feed hydraulic oil into the piston, and it applies load. And we just kept doing that until the girder failed. So this was the girder at about 150,000 pounds. This was it at about 250,000 pounds. And at about 300,000 pounds, we started to see a little bit of cracking. This was really when the girder started to fail. But after it failed, it really wasn't resisting any more load. We decided to have fun with it, and we loaded it so much that we completely destroyed it. You could actually see completely through the deck on one end. To give you an idea of how strong the girder is, when we design highway bridges, we design for a vehicle that weighs about 72,000 pounds. This one girder resisted over 300,000 pounds. So these girders are very stout and very strong, and they're very cheap to build as well. But there's a whole other assortment of issues that need to be investigated that we're going to be doing in the new structures lab in the new building. So just, a thought to keep in the back of your head if you're interested in, fabricating some large-scale specimens and loading them to failure. If that's something you're interested in, just keep that in the back of your head. I mean, my general thought is that any day with controlled demolition is a good day, but that's me. So just to conclude real quick, structural engineers, what is it that we do? We design safe and economical structures. You're going to enjoy a decent salary. You're going to enjoy job flexibility if you're a structural engineer. One of the nice things, if this is something you're interested in, you are somewhat afforded the opportunity to travel if you would like. No two projects are the same, which is an added bonus if you enjoy a challenge. And I say this about structural engineers, but this is really true about engineers in general. You're really going to be hard-pressed to find a career that contributes more to society. And if you don't believe me, just look out the window. What do you see? You see roads, you see bridges, you see water systems, you see dams, you see buildings, you see everything that comprises the built infrastructure. That wouldn't happen if it weren't for civil engineers. This is my contact information. I'm in the engineering lab over on 3rd Avenue. That's my office number and my email address. Do you have any questions? Feel free to contact me. But while I'm here, does anybody have any questions for me about engineering in general, what I do? Well, all right. Well, I appreciate your time, and thank you for having me.
All right, guys, you got to deal with two of us today. Sorry about that. I'll try and keep it short. My name is Michael. As Dr. Waite said, I graduated from Marshall. That was in 2010. To kind of give you an idea of how far this engineering department has come since then, when I started here, it was in 2006. We had 4 faculty members. We did not have any engineering buildings, let alone 1.5. We met in the basement of Gullickson Hall. If you've never been down there, please don't ever go down there. It's a bad place to be. But I've got some good memories of being there. I graduated with a class of 15, and so this is the first engineering class, but there's still over 100 people in here. So that kind of just gives you some sort of idea. It's only been 4.5 years, but how much this program has grown. So that's always cool to see when I come back. But I work at the Ray Hall Transportation Institute, and we'll kind of get into a little more about what we do here in a little bit. Like I said, I'll try and keep it short, keep it simple. If you guys have any questions along the way, feel free to stop me. I'm just going to go through what ITS is, Intelligent Transportation Systems, kind of what I do. what that looks like in the state of West Virginia, and then specifically at RTI what we're doing, and then I'll kind of give you a quick overview of one of the projects that I've played a major role in. So as we've been talking about civil engineering, you have your multiple disciplines. You have structural, obviously, which you just talked about, water resources, which is hydraulics, kind of what Dr. Waite does, geotech, and environmental as well. And so you can kind of do this with every discipline of civil engineering. You can keep breaking it down smaller and smaller. So transportation engineering even. You can get it down to highway, traffic, airport, port and harbor, railway. And so kind of where my focus is traffic engineering. And even that, again, you can continue to break that down. And what I mainly focus on is intelligent transportation systems and traffic signal design and management. So with any form of engineering, what you always start with is you start with a problem. So in the early 90s, the U.S. Department of Transportation and the FHA, Federal Highways Administration, they kind of looked around and said, we're going to run into some issues pretty soon. And so this was their forecast for traffic in 1998. This is all the highways throughout the United States. As you can see, green is operating below capacity, and then all the way up to red is exceeding capacity. So everything in that, it kind of looks all right. It's not in bad shape. But then they looked at 2020, and they were like, okay, that's a lot of red. We're going to run into some big issues. And so that's kind of where they said we're going to need a solution. So does anyone have any idea why we're exceeding capacity, or why we're expected to exceed capacity by 2020? Any ideas? More cars, more people. Exactly, but also more so than that, more cars, more people, not any more roads. And so, as you can see down here at the bottom, this line here, that's basically how many roadways we have throughout the U.S. That number's not changing, but these numbers are changing. That's the number of vehicles that are being put onto those roadways. And so they said, we need a solution. And that's kind of where ITS came from. Intelligent Transportation Systems, I'll just refer to it as ITS from here on out, just because it's easier. But it's the use of communications-based information and electronic technologies to improve safety, mobility, enhance productivity, and increase security. And so that's made up of a number of systems that focus on intelligent vehicles, intelligent infrastructure, and then the two of those working together, the integration of those. So any government agency, when they see a problem, what do? They throw money at it. So in 1991, they said, we see this problem, we need to do some research on it. What are we going to do? We'll throw some money at it. So over 6 years, they funded $1.2 billion worth of projects to kind of try and come up with some sort of solutions, to throw it out to people, throw it out to state agencies, throw it out to private agencies, to come back to them and say, what can we do to fix this? We're going to be in trouble. How can you help us out? So that funded a lot of projects, and then in 1998, again, they said, well, we're still not quite there. We'll keep throwing money at it. And as you can see, the money that's being thrown into that research has kind of decreased somewhat, but there is still plenty of federal funding that kind of goes into ITS. And so some of their early initiatives, you'll see a lot of them here. IntelliDrive, it's basically, there's a picture down here, driver safety through vehicle-to-vehicle communications. So taking a vehicle and allowing it to talk to another vehicle so they know what's going on with each other. Next generation 911. So that came in with voice over IP and no longer using phone lines and saying, okay, we're going to pipe everything over the internet. We're going to be able to send a lot more information that way. That way we know where the caller is exactly, precisely using GPS, and just kind of integrating that into a centralized 911 system. Operational testing to mitigate congestion, which again is kind of tied back to that original problem. Corridor management, electronic freight management, and then there's a few more here. ARES is a big one that you'll hear about a lot now. Basically, that's got an environmental component to it. So that's being driven by more cars on the roadway. How can we have less emissions? And it basically just means you have to move traffic more efficiently, and that's how you're going to reduce emissions. Intersection collision avoidance, national 511 deployment, that was a big one. We'll talk about that here in a minute. And so some more ongoing major activities, real-time data capture. That was a huge push in ITS as well, as how can we get more data? And now we've gotten to a point where we have a ton of data, but it's almost to a point where we don't know what to do with it. We have so much. And so that's where a lot of the research is being focused now is, okay, we got all this data coming in, what can we actually do with it? And then vehicle to infrastructure safety. So we've got vehicle to vehicle communication, but now we also want to do vehicle to infrastructure communication. So it's all about integrating everything. And you can kind of see this in this picture. This is like an ideal ITS scenario. You have every vehicle talking to every piece of infrastructure. It's all integrated into a centralized system. So like I said, 511 development, that was one of the big pushes. If you would have looked at this graph, this is the 2014 version. If you would have looked at this just 3 years ago, West Virginia would have been gray as well, meaning that they did not have a 511 system. We were second to last in integrating, which we'll kind of talk a little more about how West Virginia has been behind the curve, but they're trying to catch up. Arkansas, it's really funny to me. They're like, no, we're not going to do that. This is a federal initiative, but we're just not doing it at all. So it's something that West Virginia was not last in. We were second to last. So we're moving on up. We're doing our best. So like I said, ITS within West Virginia, we were a little bit behind the times. If you remember, the federal initiative started in 1991. By the time West Virginia got around to starting their ITS program, it was 2006. So 15 years behind already. We're trying to play catch up. But starting in 2007, that's when the deployment actually began of all this stuff. So what we had statewide traffic management center. We'll kind of examine all these individually quickly. RWIS, which is roadway weather information systems, dynamic message signs, closed circuit TV, integration with county 911 centers, and the West Virginia 511 system. So basically, for West Virginia, they were coming at this all from a safety perspective. That was their driving force in implementing ITS. And you'll kind of see that throughout. So moving on, this is in Charleston, West Virginia. We have now a statewide traffic management center. So this is manned 24 hours a day, 7 days a week, 365 days a year, even on Christmas. They get paid overtime, but they still have to be there. So this was dedicated in 2008. So basically, every piece of ITS equipment that's located throughout the state is coming back to this center. And they'll have kind of these displays, and I'll breeze through what those look like. But they have all kinds of information available to them, 911 information, accident information. This will come from weather information. It'll come from all over. And like I said, I'll show you how that kind of all comes together and what the end result is. So one piece of information is RWIS. And so this is weather information that they can get two different ways. There's stations that are located along the road, on the side of the roadways, and then actually in the roadways. It's kind of hard to see, but there's a little puck. It's about a 3-inch diameter, but it's down into the pavement, and that'll give them internal information about what's kind of going on there. So these are the locations. As you'll see, West Virginia has been very kind of critical to put them along interstates, not so much. There's a few throughout here along state routes or county routes, but really the focus of West Virginia has been on interstate routes, and you'll see that throughout everything they've done. So this is kind of, it's hard to see, it's a lot of information, but this is the information that you get out of every one of those sensors. So you can get external temperature, you can get internal temperature, dew point, precipitation, whether there's any rain or snow going on at that point. Some of them have wind information coming in as well. So a lot of different capabilities, and like I said, they're located throughout the state. All that's coming back to the Traffic Management Center. Closed circuit video cameras, they've got those as well. This is a familiar exit, Hal Greer here. You would never know it, but there's a camera located, it's right here on that. And so this is kind of the view coming back. Sorry, let me stay on that for a second. So again, all these cameras are coming back to the TMC. They're located throughout the state. They have full zoom capability on those cameras. They can zoom in and look at your license plate. Not that they're not doing it for any reason, but it's more so when an incident occurs, they'll kind of zoom in on that location, see what's going on, so that they can get information out to the public about that. Those are located, again, they're heavily along the interstate corridors. They're starting to integrate them into major U.S. routes. You'll see a couple on 19 here, but it's mainly on the interstate. Dynamic message signs. So this one, it's blank right now in this picture, but that's where you've all driven down the roadway. Sometimes it's helpful information and sometimes it's not. They're trying to do a better job about that. Sometimes it's old information. You'll see wreck at mile marker 28 and you drive by mile marker 28 and there's nothing going on. So that's part of this initiative as well, is trying to clean that up and trying to do a better job about getting relevant information out to the public. So again, along state corridors, mainly the interstates. So this is the West Virginia 511 system. So if you go to www.wv511.org, this will be the display that you see. Anyone can access this. It's open to the public, and you can get to any of this information. So it'll give you, the green means traffic is flowing well. It'll give you traffic conditions throughout the state. If there's a message, you can barely see it, but there's a message on that dynamic message sign. And so you can click on that and pull it up and see what's going on there. You can actually pull up any of these cameras. If you click on the camera, you can go in there and you can watch traffic. If you're bored, feel free to do that. You cannot move the camera or anything like that. You have no full control, but you are able to observe what's going on. And at any point, the people in the TMC kind of they can take that control away. What they'll do, generally when there's a wreck, they'll turn those cameras off to the public. That way, they can view what's going on, but the general public can't sit there and kind of check out what's going on at a wreck. That just becomes a security issue for people. So again, all kinds of information on there. There's also planned events you can look at. So if there's planned construction along a route, that'll show up on there. You'll see here there was an incident right there. That means a crash occurred there and there's something going on. So before you leave, if you're going on a long trip and you're going through West Virginia, go on there, check it out, or you can just call 511 from your phone at any point. So it's a good system. We were a little behind on it, but it's finally here, and it's been well received by the public. So again, this is kind of the flow of information. You've got information in and then information out. So all your information coming in, if you'll notice, this picture is not from West Virginia, and some of the words are not accurate, so don't grade me on that. But you've got police information coming in, phone calls coming in, all your cameras, your contractors, your road reporters, and weather coming in. And then again, all that's broadcast out. That's broadcast out to the 511 website. It's broadcast out to the 511 phone system, dynamic message signs, and any traffic control that's necessary. So that's ITS kind of all being tied together. So again, some of the challenges throughout West Virginia that we've had is the communications infrastructure and the geography. Just being a mountainous region, it's harder to get communications from point to point. Funding is always going to be an issue. Again, like I said, everything in West Virginia has been kind of safety driven. So if they don't see it as a safety concern, they're less likely to kind of give money to that, even if it is shown to kind of improve the overall traffic flow or driver experience. So the future of ITS in West Virginia, adding additional field devices, integration of additional 911 centers, that's back to the traffic management center, and just technology continues to evolve every single day. We all know that, but that's true in ITS, that's true in everything. So just kind of continuing to evolve along with that and not being 15 years behind like we were at the beginning. So ITS at RTI, I'll talk about this for a minute. So the Ray Hall Transportation Institute, what that is, it's a university transportation center. And so what that means is a lot of our funding is federal funding, and then everything else is project-based. So everything we do is research-based. We do specifically a lot of projects with the West Virginia Department of Highways. We've worked alongside of them with a lot of these ITS deployments, and so that's kind of what you'll see here. We do, at RTI, we have a satellite traffic management center. You'll kind of see that down here. So it's not to the scale of what they have in Charleston, but we have access to all the same information coming in except for the 911 calls. So those aren't coming into where we're at. But that center was established there as kind of an emergency in case anything ever happened in Charleston, and also as a training center. If they ever want to use it to bring new technicians in and train them in Huntington, we're capable of doing that. And there's one more satellite traffic management center that's along the interstate between Beckley and Charleston. There's one more in between there, the Turnpike. And so the major thing that we've been doing with the West Virginia DOH is traffic signal management. And so we have some that are centralized, and I'll talk about that here in a minute, and then also just a statewide management. There's about 1,300 traffic signals in West Virginia, and we just started a project with them about 5 or 6 months ago to kind of manage all of those. So it's a big undertaking, it's a lot of work, and we're still kind of sorting out what our process is going to be for that. But we've been managing some of these other systems before then. Morgantown has been about 5 years now, and Huntington, which is the one I'll focus on just because it's the most relevant to you guys who actually live in Huntington, and you'll be able to kind of see some of that. So in order to talk about a traffic signal management, I want to just give you a very, very brief overview of what is in a traffic signal, what kind of makes it up. So whether or not you've ever paid attention, at every traffic signal there is a traffic signal cabinet, and that's along the right-hand side here. It's a big silver box. It'll either be on one of the poles or it'll be on the ground. And in that there's a lot of equipment. You've got your traffic signal controller. There's a few other things. I'm not going to get into details, but you've got we call that a conflict monitor, sorry. And then you've got load switches down here. Basically, you got a lot of wiring, everything coming in. Every signal head has a red, yellow, green wire. Those all have to come in there. So just a lot of wiring coming in there as well. So those are some of your components. You've got more components. You've got detection. I'm sure you've noticed along some of the intersections in Huntington, we've got video cameras. I've had a lot of people ask me, are those red light cameras? No, they're not. They're just detection cameras, meaning they're sensing whether there's a vehicle there or not. And so when there's a vehicle there, that camera will send a signal to the traffic signal controller and say, hey, there's a vehicle here. We need to turn that phase green. So that's all that's doing. It's not taking pictures of you. It's not seeing if you run red lights. That's not to encourage you to run red lights, but just know if you accidentally do, you're not going to get a ticket for it. And also for future reference, if a city is using red light cameras, they have to have signs up. So that's an easy way to get out of a ticket. If there's ever not a sign and they're using red light cameras and you get one, just know that. You're good. Inductive loops. So I'll talk about those in a minute, but basically right here you'll see kind of as you approach an intersection, sometimes you'll see they saw cut out. Basically all it is, let me come back. Yeah, so it's the most common type of detection. Basically, it measures inductance. So it's basically like a magnet. So when a car's over it, it says okay, and it sends a signal to the controller. So that's all that is. The problem with loops is because they are cut into the pavement, they're susceptible to, if that road is repaved, then you have to put the loops back in. And a lot of times you'll get weather issues with them, like if water gets in there, it's supposed to be sealed, but a lot of times that sealant doesn't take for multiple years. And but that's an inductive loop, if that answers your question. So older types of detection, and this is just a fun fact, but this is 18th Street. You'll see these old, they're basically pressure plates. So that was one of the early forms of detection. Just it would depress as a car went over it. These have been here for at least 20 years. It's amazing to me that they've never been removed, but you can still kind of see them. Now they're basically just a hassle to drive over for you. But now you can tell your friends what they actually are, that there used to be a purpose for them, and they're not just random rubber plates in the roadway. So this is, again, video detection. That's what's used in Huntington. This is kind of what the display looks like. As a vehicle enters this zone, it'll be detected. These bars will go green, and again, that sends a signal to the controller saying, hey, there's a car here. And so you can do multiple lanes. You can tie those lanes together. or you can just do, you always want to do individual lanes just because obviously cars are only going to come in one lane at a time. So some of the problems with video detection, if these zones aren't set up right, a lot of times you'll have a car sitting here, but it's not on the zone on the camera, so you can sit there and no call will ever be placed. And again, susceptible to weather, like if you have fog, generally the camera can't see through that, and so that creates some issues. Basically, there is no perfect detection system. This is a newer one that we used in Morgantown. They're magnetometers. So again, kind of, they're using the same technology that a loop would, but it's just on a much smaller basis. They're about the size of a hockey puck, if you can envision that, and they're just drilled down into the roadway. And again, they detect that vehicle when it's sitting over it. And the last and newest form of detection is radar detection. So those will kind of use the heat signature of a car to detect it. They're not being used very much in West Virginia. It's a newer technology, like I said, and we're kind of always behind the curve on that. But there's a couple systems that the DOH is using those on. So I'm going to breeze through this quickly. Just stop me if you have any quick questions, but I know you guys are trying to get out of here, so I won't keep you late, don't worry. But the old Huntington system, there were a lot of issues with it. It was installed in 1989, and so in 2011, they came along and they said, okay, we're going to redo this. But how bad it was, we did some travel time. We've got a GPS data collector, and you kind of just stick it in your car, and as you drive down the roadway, it collects your time and your position. And so these are, the red and the blue are the routes that we collected. So how bad was it? This is an ideal travel time, 300 seconds. This is going on 3rd Avenue from 31st Street all the way down to 1st Street. So that's what it should be if you drive the speed limit the whole time. But we were getting stopped at Hal Greer a lot, stopped at 13th a lot, and basically it ended up being 2 to 4 minutes of delay each time down through there. Now that doesn't sound like a lot, but if you are running late and you need to be there, 2 to 4 minutes turns into a long time. But also if you add up the cumulative time, if you drive that same route every single day, you're going to get pretty tired of being 2 to 4 minutes longer than what it should be. So again, in 2011, they came along. It was a $3.67 million project. They said we're going to redo these 59 intersections in Huntington. They completely stripped most of them to the ground, poles, cabinetry, signal heads, detection, everything. So basically starting from scratch. And so now we're moving into the new age with what they did. We've got a centralized management software. And so basically what that means, and I'll show you how this kind of all comes together here in a minute, but I can sit at my desk. This display is real time. There's communications back to the intersection, so I can see what's going on at every intersection in Huntington, and I can also upload and download from the controller, which means I can send changes out if I ever want for like a football game, for example. That's a special event, so I can change the timings for 2 hours and send that out to the controller just sitting at my desk, rather than having to go out to the field, which is what you would normally have to do, and do it intersection by intersection. So that's really helpful. Huntington, it wouldn't be as big of a deal, but for a system like Morgantown that we're managing that's 3 hours away, it's really nice that I can just sit at my desk rather than driving 3 hours there and 3 hours back just to make what could end up being a 5-minute trip to the field. So the communications, what that looks like in Huntington, there's a radio at each intersection as well. You may or may not have seen those, but each intersection's talking to each other. So this is 26th Street on 5th Avenue and 29th Street on 5th Avenue. So those radios are constantly in communication, and then that'll come back to a master intersection. So there's a lot of information here, and I'll try and make the most sense of it. So you've got an individualized intersection. So again, everything's coming back to the controller, your signal head, your monitor there. You've got pedestrian signal, all of this information, your video camera, all that's coming back to the controller, and then that is talking to just a ruggedized switch, and then that's going out to the radio and talking to the next intersection. And again, there's a main intersection, and that's where all the information from every signal is coming back to one master intersection, we call it. And then that information is going out over the internet. It's going to a data center in Tays Valley, sitting on a virtual server, and then I can access that server, or anyone else can that has the proper credentials, obviously, can access all of that information from anywhere. All it is, it's a remote desktop connection over a VPN. So it's a pretty simple setup, but again, there's two-way traffic, so I can talk to each individual intersection, and that intersection can talk to me as well. So it's pretty incredible what we're able to do with that, the changes we're able to make just sitting at our desk. So as we look at this, we said, okay, what are our main corridors? How can we make travel time better? So obviously 3rd and 5th Avenue are your main streets in Huntington, and then we also picked out some secondary streets. And just to kind of give you an idea of what it looked like after we got done. So this is the travel time. The blue is kind of inconsistent travel times before we started, and then red is after. So we reduced travel time by 25%, and the variation, which is the bigger factor of that. So it's a more consistent travel as you go down 3rd Avenue, as you go down 5th Avenue. You should be able to hit every green light along the way. The user benefits, we kind of put a number value to time and said time is worth this much, each minute saved is worth this much. So it's an approximate savings of $1.7 million per year. That's cumulative for every user. So that takes into account fuel cost and, like I said, just your time. I'll stop here just because that's kind of the end of our time and the end of what I have for Huntington. But does anyone have any quick questions for me before Dr. Waite lets you guys get out of here? You got anything, Dr. Waite?
Thanks a lot, Michael.
All right.
Appreciate you coming today.
No problem. You guys have a good day.